Hello, this is Eric White. Well, at long last, after going through a lot of other screencasts to cover preliminary material, we are now ready to talk about recursive pure functional transformations. It's been a fairly long road to get to the point where we are, but now we're here. This is where the really fun stuff starts. I want to give a little bit of a deeper explanation of the motivations for learning recursive pure functional transformations. One area of study is something called performance load. And performance load is made up of two separate components. There's cognitive load versus the kinematic load. So this is just a fancy way of saying that what it takes to do something, you have to know a certain amount in order to do it, and then you have to do a certain amount in order to accomplish that particular task. And we can talk about the cognitive load of these types of transformations. And the first thing is that you have to know about lambda expressions. You have to know about lazy evaluation. You have to know extension methods. You need to know the detailed semantics of XML. You need to understand the semantics of link to XML. And on. These are all the topics that we have covered up to this point. And there's a fair amount of material there. To be honest, we haven't gone into the depths of every one of these topics. We've covered them to a certain amount, but there's still more to learn, no doubt. But our whole goal in having a larger cognitive load in writing these types of transformations is to reduce the kinematic load. And really, we're reducing two things. The first thing is we're reducing the amount you need to type. In other words, typing 3 lines of code is much better than typing 30 lines of code. And if you can look at those 3 lines of code and understand what they're doing in an easier way, then that actually is part of the reduction of your cognitive load. That you can start to read these types of queries the same way that you would read old styles of code, the way you've been writing code to date. There have been studies done where they've determined that the number of bugs in a particular application or in a particular chunk of code is directly related to the number of lines of code, or more technically accurate, to the cyclic complexity of the code. Because of course you can add more lines of code and not actually increase the complexity of the code. So part of the kinematic load that we are attempting to reduce is we're making it easier to do debugging. If you can write more accurate code, then you have less debugging to do and you can be more productive. That's our goal in writing these types of transformations. Well, enough of talking about this. Let's go look at some code. So what are we really doing when we're writing a recursive pure functional transformation? What we are doing is we're cloning an XML tree. Now, if you'll remember back to the screencast on functional purity, one of the things about functional purity is that you never modify anything. That if you can get to a particular variable, in other words, if that variable is in scope, then that variable has the value it has and it's never going to have a different value. That's one of the key points that makes functional programming doable. If you are modifying state while you're writing your query, your programs become very hard to debug, very hard to understand. We don't want to do that. So we aren't modifying these XML trees. What we're going to do is we're going to take one XML tree and we're going to transform it into another completely new XML tree, and that's going to be the process of doing our transformation. Now, there are certain transformations that I have written, such as the transformation to accept tracked revisions. It's actually 7 successive transformations because you can't do everything in a single transformation. That what you do is you transform it one time to another form that's easier to use, and then you transform it again, and then sometimes you have to do one transform before you do another transform because you might want to be eliminating empty runs or something like that. Writing a recursive pure functional transformation doesn't mean that you have to do the whole transformation in a single step. You can do it in incremental steps. Sometimes it actually is significantly easier to first transform the word processing ML into another form that's easier to work with, then do the transform that you're actually interested in doing, and then transform back to a more canonical form or a more standard form. We'll talk about those approaches later. An example of those is that at one point in time, in order to do certain types of modifications of word processing ML, I first transform a paragraph in such a way that I have as many runs in that paragraph as I have characters in that paragraph. In other words, every single run in the paragraph has a single character. I can then do all kinds of interesting things. I can insert comment start or comment end markers wherever I want to, or whatever. I can make very interesting modifications to that paragraph, and then I can, after that, write code to coalesce all adjacent runs that have the same formatting, and then the markup comes back to a more standard form of word processing ML. That's an example of writing successive transforms in order to make your job easier to accomplish your larger goal. So we're going to clone an XML tree. One last point is that certainly it's the case where doing these successive transformations creates a lot of short-lived objects on the heap. I've talked about this in previous screencasts. The garbage collector in C# and in fact the garbage collector in JavaScript both have the characteristic that they perform well with short-lived objects on the heap. There's some interesting information out there about how those garbage collectors work, and we don't need to dive into that information at this point in time, but suffice it to say that it works okay to create a lot of short-lived objects on the heap. So let's create a little element and let's clone that element. So here I've created a little element. It has a root element, it has two attributes, and it has a child element with the name of text, and that text element has a text node in it with the contents of ABC. And if I look at the result of running that little program, we can see the little bits of XML that comprise that particular XML tree. So what do we have to do when we are cloning an element? There are only two things that we have to do. An element only has two things. It has attributes and it has nodes. That's the only thing that comprise an XML element. So I can make a new element. First of all, I want to have it have the same name as the first element, so I can put e1.name as its name. And then I can include all of its attributes, so I can put in e1.attributes. And I can include all of its nodes. And if I print e2, we'll see the exact same XML. So in other words, I've cloned that E1 element. I've made an E2 element that has the exact same contents. But there's one little problem with this, is that when we've cloned this XML, we have retrieved the child nodes of the E1 element through this e1.nodes expression, and that returned the child X element with the name of text. That's all fine and good. But what this did is this made use of a particular characteristic of linked XML, which is the issue of cloning versus attaching. So this e1.nodes expression here returned the actual child element of root, which is this element named text. The linked XML constructor looked at that text element and saw it does have a parent. Its parent is this root up here in E1. So because the linked XML API saw that that particular child element that we're adding has a parent, the linked XML API then clones that child element and adds it to E2. That's all fine and good, but it meant that that text element and the contents of that text element are cloned without us having any control over that cloning of it. So let's make a change to this program. So I'm going to write a bit of code here to do this in a different way. I'm going to write a method called transform, and this method will be a static method. I'm going to have it return object, and I'll talk about why it needs to return object later. I'll call it transform, and it's going to take an X node argument, and I'll call that argument node. And inside this method, first thing I'm going to do is I'm going to determine whether the node that comes into this method is an X element or not. So the way I'm going to determine if it's an X element or not is I'm going to use the as operator in C#. I'll define an X element, I'll call it element, equals node as X element. And what this statement does is if node is an X element, then it casts node to an X element and assigns element to the value of node. But if node is not an X element, then the element variable here is assigned to null. That's the semantics of the as keyword. You could do a test against the type of X element and then do a cast, but the problem is that's not as efficient inside the .NET virtual machine as using the as method. The operation of casting is a fairly expensive operation, or a somewhat expensive operation. So if you use as, that's twice as efficient as testing the type and then doing a cast. So we'll use as in that case. And now I'm going to write some code that I'll say if element is not equal to null, then I'm going to do something. And if element is equal to null, then I'm going to return node. Now, if element is not equal to null, that means that we have received an element as this variable node, this argument node coming into this method. And I am now going to fabricate a new X element from the X element that was passed to transform. So I'll create a new X element. I'll name it with the same name as the element that was passed into this method transform. And as we talked about before, elements have only two components to them. The first are attributes and the second are child nodes. So let's include all of the attributes from the source element in our new element. And the way to do that is put in the expression of element.attributes. And now I want to include all of the child nodes of that element in our new element. So I'll put in the expression element.nodes. But these nodes may themselves be elements that need to be cloned. So what I'll do is I'll dot into the select extension method, and I'll name my argument to the lambda expression as n, and I'll call this very same method, and I'll pass n to this very same method. So now I have written a method. It's a grand total of 2, 4, 6, 8, 10, 11 lines long, including some lines that only contain braces. And this transform method will take an X element as an argument, and it will return a new X element, and that element will be cloned, and every element further down in the tree will also be cloned. And this is why we call it a recursive transform, because in this select extension method, we're calling back into our transform method. So now I can modify our example down here, and I'll call transform of E1. But there's a minor problem, which is transform returns an object, and we'll talk about that later. So I need to cast the results of this to X element. Oh, I forgot one thing. I created the new X element, but now I need to return it. Okay, so now we've got a complete program that will first new up a X element in this variable E1. It will then clone the entire X element into a new X element, and every child element and every child node will be cloned the whole way down through the tree. And if I run it, we see what we expected to see. It looks exactly like the original XML tree, but it is in fact a new tree. And this is what we call the identity transform, that this little bit of code here will transform any XML tree into a new XML tree where every single element in the tree is cloned. Now, just for comparison, here is the exact same program using the ltxml.js library, in other words, the linked.xml for JavaScript library. Up at the top of this HTML page, this is just boilerplate stuff that you have to have in order to make a linked.xml program work in JavaScript. And if we scroll down here we can see the exact same program that we had in C#. We have our transform function. Of course, I've changed the casing of all of the various things here to conform to the JavaScript conventions. So transform should be lowercase. The method here, attributes, that should be lowercase. The method nodes and the method select, those are lowercase. Another thing, in JavaScript, we don't have the as keyword because we don't even have types in JavaScript. So the equivalent way to do what you want to do here is you test that the node type is equal to this string of element. And if the node type is equal to the string of element, then the example will execute the code that it needs to run in order to clone that element. And otherwise, down here, it returns node. And here is the code to use that transform function. First of all, the code news up the E1 variable with the exact same XML tree that we had in the C# example. And then the code sets the variable E2 equal to the results of calling transform passing E1. And again, because JavaScript isn't typed, we don't have to cast the results of the transform method to xElement. It's not required. And then down here at the bottom is the code to dump out E2. And of course, a couple of things. We have to call this method convert to entities because if you simply output the XML in the middle of a pre-tag, you can see up here that all of these script elements are within the pre-tag. If you simply dump out the XML will be interpreted by the browser and it'll put out gibberish. So what we have to do is we have to convert all of the less thans and greater thans to entities, and then we can write the results of that to the browser. And if we run this little example, we see the exact same results that we saw in C#. So first key point is these types of transformations work equally as well in JavaScript as they do in C#. But the next thing is I did this for a particular reason in JavaScript because I'm going to go modify the linked.xml library here a little bit. I'm going to go find the xElement constructor. Here is the xElement constructor in the linked.xml library for JavaScript. And I'm going to modify this constructor a little bit. I'm going to dump out the name of the node that it is currently constructing. And I'm going to do this for a particular reason. I'm going to call document.writeLine, passing this .name. I'm also going to do it down here. So this way, before it returns from this method, it's going to dump out the name of the element that is currently constructing. Now I'll come back to my example here, and I'm going to run it. And what we see here is we see text followed by root, followed by text, followed by root, followed by text, followed by root. And let me explain what that means. What it means is that it is actually constructing the tree from the bottom up. When we clone the tree in that fashion, the first element that is constructed is the text element, and then the last element that is constructed is the root element. If we look at our example, we can see those three occurrences. The first occurrence here is when we created the original tree. It created the text element and then created the root element. The second time we saw text and root is here where we called transform, and it first printed out the text element name and then printed out the root element name. And then the interesting thing here is when you call toString in the JavaScript implementation of link2xml, it actually has to clone the tree one more time. And there's specific reasons for that. In order to make it serialize properly, it has to clone the tree because it needs to modify the tree before it actually serializes the tree. The key point here is this transform method clones the tree from the bottom up. Let's modify the tree a little bit and then we'll see more examples of this. So I am going to I'll call this text 2. I'm also going to call document.writeLine here. So now I've modified the XML tree. The source XML tree has this root element. It has 3 child elements, text, text2, and text3. And text3 has further another child element itself, which is level 3. So what we're going to see is we're going to see first text, then we're going to see text2, then we're going to see level 3, then text3, and then finally we're going to see the root element be constructed. So let's run it. And here we can look at the before transform. We see text, we see text2, we see level 3, we see text3, and then finally we see the root element being constructed. The point about this is just to know this is the order in which things are put together when you clone the XML tree. It clones it from the bottom up. Let's go back to the C# example. So now we've seen how to clone a tree without making any modifications. Now let's do one little modification to this and let's change it so that we are transforming the tree in some small way. So now in the C# example, I've modified that XML tree. This XML tree now has the situation, it has a root element. That root element has 3 child elements. There's text1, text2, and text1. And the third text1 has a child element of level 3. Let's say that we want to rename every text1 element and we want to change its name to T1. So what I can do is I can come up here and I can say if element.name is equal to text1, I'm going to return a new X element. I'm going to call the new X element T1. And of course, I am going to return all of the attributes of whatever element we're cloning. And I'm also going to push all of the child nodes of this element through the transform. In this particular case, I didn't assign it to a variable new element. I simply returned the new element as I newed it up. We can change this one to make it so it's more orthogonal. So now this transform takes the following action. Any time that it sees an element with the name of text1, it's going to new up a new element with the name of T1, and it's going to make that new element have all the attributes of its source element, and it's going to take all of the child nodes of that source element and push them through the transform too. And down here we have cloned E1 into E2 with the exception that text1 is going to be renamed to T1, and then we have printed out E2. And if we run the program, we can see exactly what we expected to see, that XML tree was transformed. Every text1 element was renamed to T1, and everything else remained the same. So that text1 element that had a child level 3 element, that element came through just fine. It was cloned without any problem at all. And if the element name wasn't text1, then this particular cloning cloned those elements without any modification at all. And that was accomplished by the identity transform that occurs below the conditional transform that changes the element name from text1 to T1. So here's the thing. This isn't really that awfully complicated. If you look at this, there's not an awful lot of code. We've got maybe 20 or 25 lines of code here that transforms an XML tree and then changes the name of one of the nodes wherever it finds it in that tree. It does require a certain amount of background information, but in the end, the code is really pretty simple. In the next screencast, I'm going to show how to transform a tree such that we're going to eliminate a node from the cloned XML tree. Until next time, see you later.